Thank you. Now we will have a few talks, short talks about data processing, rather, and we will hear about explainable machine learning on an instrument which is very dear to me, a NaCo, an old instrument, but VLT, by Markus Bonse from ISO.
Hello and welcome. I'm Markus Bonse. I'm a postdoc at ISO. And today I want to show you how you can use methods from explainable machine learning to dig very deep into noise of archival data to find some hidden treasures. And if you process high contrast imaging data, you end up with a residual image like this most of the time. And then you're wondering, is any of these objects or these blobs like a real planet? And in this case, I actually inserted something for you. So this is a little warm-up quiz. And I want you to pick one of these 4 options. Okay, so this is the solution. If you did not manage to find the right object, don't worry. By the end of this talk, I will show you a method that can turn this residual image into this. And then it should be very easy for you to identify the real source. Okay, so let's have a step back. How do we distinguish speckle noise and planet signal? And one widely used method for this is principal component analysis. And PCA has this tuning parameter, the number of components, which gives you some freedom to reduce the strength of the noise. In reality, it's really difficult to find the right number of components, as I can show you in this data set. So it's again 2 fake planets. It's again NaCo L-band data. 20 components, you don't really see the companions. At 60, you reach the highest SNR for the inner one, and you actually need to push to 300 to get the highest SNR for the outer one. And a priori, you don't really know what is a good choice, and you can boost the SNR of many speckles above 5. That's not an issue. Okay, so, but what is happening here? So on the right, the inner companion is lost. And this is known as self and over subtraction in angular differential imaging, but it's not only this, it's also something intrinsic to principal component analysis. And this motivated me for this project to use some methods from explainable machine learning to understand better of what is happening in PCA. Because ideally, we want to be on the right. We want the strongest reduction of the speckle noise. Okay, so what is happening in PCA? In PCA, you have on the one hand the raw data, and on the other hand, your noise estimate, which is built by projecting the raw data into a low-dimensional space and reconstructing it. If you lose part of the planet signal and you take a pair of images, you know that at least some of the signal needs to leak into that noise estimate. And now you can use explainable machine learning to ask the question, which information was used at the position of the planet in the noise estimate to calculate the noise at that position? You can do that by so-called using input gradients. They will give you a heat map of where the information is coming from, and then you get something like this for PCA with a lot of components. And as you can see, most of the information that is used is just coming from the position where the planet is at. So essentially, we are just copying the signal of the planet from our data into our noise estimate, subtracting the planet, everything gone. The interesting part about this is it's not really linked to where the planet is at in your data, but you can do the same exercise for other positions. You always get the same image. It's actually looking fairly familiar because this is just the telescope point spread function. So what's happening here is if you push to a very high number of components, PCA learns the telescope point spread function. And that's a really good model for the speckle noise because the speckles will look like the telescope point spread function. There's only one issue. Planet also looks like the telescope point spread function. So we get rid of basically everything in our data if we push to high components. And this result motivated me to build a new post-processing method that overcomes this limitation of PCA. And I call this method signal safe speckle subtraction, or 4S, or FORCE. Okay, so in the interest of time, I can only give you the key ideas and maybe give you some ideas of what is good data to use FORCE on. So the first idea is you put some constraints on the model to make sure that you're no longer learning this point spread function shape. And this forces the model to explore other areas in the image. And in this case, you see these very strong point symmetries, which are unique to the speckles and not to the planet signal. This only works, or this is only effective, if you actually need to push to high components with PCA. So if your highest SNR is already reached at 5 components, this trick will most likely not be beneficial for you. So it's really effective on data sets where you have a lot of frames and you can actually really push with PCA to very deep limits. And the second trick is a new formulation of the loss function to make it invariant to the signal of the planet. And this trick makes use of auto-differentiation through image rotations, so in PyTorch. And in the end, this is most effective if you have a lot of field rotation. So if you have a data set that is very long, much of frames. So if you have a good data set already, it makes your good data set even better. Okay, so if you have such a data set, you can get really big improvements of more than a magnitude, especially at small separations. And this motivated me to start the time to use the force. And I also want you to use the force because the force is on GitHub. Okay, so one question that I asked in the beginning was, is there any object that was found with sphere or new instrument that was not discovered with older NaCo? And one such example is AFLab. So AFLab was found like 3 years ago, but there's also even older, like from 2011 data. And if you process this with PCA, you don't really see any companion. If you run force, you find the companion, but on the other side of the star. And this is really cool because you can now do a really precise orbit fit, and in this case, we managed to constrain the eccentricity. There's some direct science outcome. Is there more hidden treasures in the archive? And this was kind of like the start for an entire reanalysis of the complete NaCo archive. So this is what I did. I processed the entire NaCo archive of all L-band ADI data, lots of work and pre-processing. In the end, it's more than 700 data sets of more than 500 stars. And I can't do this alone, so we organized a little workshop in Zurich. We implemented this tool, Catnip, to go through the residual images of force and of PCA. And the first thing that we noticed is AFLab is not the only thing that was overlooked. So we found another 5 more objects in the archive for which we now have L-band photometry, and we can extend the baseline in the astrometry. And we found a lot of new candidates. We wrote a follow-up proposal with ARIS to observe the objects in the same band, in L-band. And while we are still waiting for a lot of this data, because ARIS is often broken, I want to show you some first results. There's nothing in the ARIS data. And the companion that we had in NaCo was already really convincing. So what is happening here? So first of all, there's 10 years between the epochs. So it's well possible that the companion moves behind or in front of the star and we miss it. But how good are actually the ARIS limits? So I computed the contrast curves for this, and the ARIS limits are not deep enough to reach the NaCo limits from like more than 10 years ago. Why is that? We knew from commissioning that ARIS can outperform NaCo if we compare vortex data with vortex data, but actually most of the candidates are in non-coronagraphic imaging, while ARIS only had the vortex coronagraph commissioned at the time. And this is where the archive becomes handy again, because we can also learn something about instrument performance based on this huge amount of data. So what you can do is you take stars, or you look for stars which have observations in imaging and with the vortex. So you have the same star, then you cut, you have the same field rotation and the same air mass, and then you compute contrast curves, you get the difference of the two, and in total we can do that for 14 stars which are in the archive which have both. So you even average over different observing conditions. You accumulate this, and this is what you get. So if you're above the black line, the vortex coronagraph outperforms normal imaging. It does not outperform normal imaging. So irrespective of if you are close to the star or if you're further out, there's no improvement. And that was a bit surprising for me, because we knew, at least from theory, that there would be some improvements, at least in contrast. So we had a bit of a deeper dive into that, and I want to give you some first results on that. So in the background regime, the numbers for NaCo are quite severe. So 1 hour of imaging, you need 6 hours or more of vortex data to reach the same sensitivity limits. So that's pretty severe for large surveys. In ARIS, the values are better, so only a factor of 3. And based on simulations, we noticed that the key driver for this is actually the design of the Leo stop, which was very unfortunate, suboptimal for NaCo, still not really good for errors. And we took these lessons learned to redesign the masks for emitters that we are not running into the same issue again. So that's for the background regime. Contrast regime, that's much more complicated. And what is happening here, so we know, this is actually some real data, we know the raw contrast with the vortex coronagraph is significantly better than without it. So something between the raw contrast and the post-process contrast is going wrong. And this gives rise to the question, how effective is our post-processing on vortex data and on imaging data? So this similar plot as I've shown you multiple of them now. On the left is the comparison of PCA versus classical ADI. So how much do I gain by using PCA on imaging data? And on the right, the same for the vortex. And as you can see, at small separations on the imaging data, you get really a big boost in post-processing, which for some reason is not there in the vortex data. And this gives rise to some changes of the speckle statistics because PCA is modeling covariances in the data, which maybe are not so easy graspable in the vortex data. So in the end, PCA has really a hard time dealing with the vortex data, which leads to this difference in performance. Okay, so, and also I think a really big lesson learned from this is just because you get better raw contrast doesn't mean you actually get better post-process contrast. And if you are thinking about new instruments, we should really think about post-processing from the very beginning to make sure that we have synergies and not anti-synergies for our data. Okay, so if you want to learn more about this, I have some more results also for errors. It's still work in progress. Come talk to me. You can also come talk to me if you want to use the force. If you want to have some pre-release access to my pre-processed NaCo search, or if you want access to some code to process errors, NICS data, and the CutNip tool to annotate residual images. Thank you.
Thank you. Yeah. Okay, so you start.
Jules Fowler from UC Santa Cruz. Thank you for a super interesting talk. When you were talking about the vortex potentially like disrupting speckle statistics and making it harder to do post-processing, do you think that's specific to a vortex, or do you think that that would be shared with any kind of coronographic mask?
So in terms of this, so the answer is I don't know because I've only done the experiment for the vortex. We've done similar experiments for the background sensitivity for the APP coronagraph, and the vortex is doing much, much better in sensitivity than the APP. What is happening in terms of contrast, I don't really know. Yeah, I mean, this is still quite new, and I think there's probably different explanations for this. On errors, we know that there is some tip-tilt errors still, and the vortex is quite sensitive to these errors, so it might be due to this, but stay tuned, or if you're interested, go and find the answer. Yeah.
Anthony? Okay.
Should I go first? Okay. Jean-Baptiste, UC San Diego. I mean, impressive work. Amen to better raw contrast, different than post-processing. I'm just wondering, how deeper do you think you can still go? What is your fundamental limit? Or do you know? I know it's hard to determine, especially on the ground, but do you have an idea of how deeper we might be able to get from better post-processing?
Yeah, so my hope is that especially for the vortex coronagraph, that the method that we are using at the moment are maybe not the right choice. So that especially this problem of having not the contrast at small separations is actually something you could solve. So for example, the response of the vortex to tip-tilt errors is nonlinear. PCA is a linear model. So if we know what the response is, we could maybe use some kernel PCA or some nonlinear methods to build something very specific for these observations. So I think, especially for the vortex, there should still be something to gain. And this is all ADI. And if you use large transformer models even, I'm pretty sure you can go deeper. Especially on the old data, where your AO is not so good, there's a lot of NCPAs. I think the gain in post-processing on newer instruments will be smaller because the optics is so much better.
One quick question. Okay.
Yeah. So, Eric Ives, University of Hawaii, do you think there were, first of all, I have to say that the force was very strong with this talk. The data set that you used with NaCo, do you think there was something specific to that data set or the survey or the parameters of the measurements?
So which data set are you talking about?
The original NaCo data set that you...
Of AF Lab?
Of the survey that you performed then, the reanalysis of the archival data.
Okay, so I picked all data that has pupil tracking in L-band. So there's some data which has the coronagraph. It's unfortunately the larger part. And then there's especially the older data, like the AF Lab data, that is taken in imaging. And the strategy of these surveys is very, very different. There's 100 different program IDs in that. So you have everything from follow-up of accelerations to blind searches to unique things.
So you think this is potentially very applicable to other instruments, and there's nothing special about the data set that you use. It's very heterogeneous.
You mean the algorithm, the force?
Then,
So I have a slide for this.
No.
Okay, I show you a slide.
Talk to you later.
I show you a slide afterwards.
Yeah.
Yeah, short answer, you need a lot of frames, you need a lot of speckle diversity, and you need good field rotation, then you benefit. So not so much for James Webb and NIRCam and EMIRI, I think.
Okay.